Okay, so this is the final part of the week 4 lab that you'll be experiencing. You'll be using the Bode analyzer in Elvis, and this is what it looks like, except that this is a picture that I got offline, off the internet, of an RC network, but it's configured to be a high-pass filter instead of a low-pass filter, which is what you're going to be using. And so what you're going to be seeing when you run your Bode analysis is going to be something that looks like this and comes down kind of like that. And so the other part of it is that what you'll also be seeing is that the phase shift down here, it goes from 90 down to 0, but on the picture as shown. But what you'll be doing, what yours will be doing, is going from starting at 0 and going down to minus 90 degrees. And this is the minus 45 degree part right here, and I'll be talking about that a little bit later. Basically, we are looking for, and you are asked to figure out where the minus 3 dB point is on the magnitude scale. That would be up here. Where is the minus 3 dB point in this graph here? And so the question is, why are we talking about the minus 3 dB point? Well, it's because of this. When there is a convention that says frequencies that are less than or equal to minus 3 dB in a low-pass filter are in the pass band. In the pass band, meaning that those frequencies make it through the filter and get out the other end, are in the pass band. And frequencies that are greater than the minus 3 dB point in a low-pass filter are in the, what they call it the stop band, or they might call it the reject band or something like that. It's not really stopping, because you can see over here that it's not going to, it's not going to 0. They are attenuating the signal, the frequencies that are higher than the 3 dB point, and I should write here that this is a 3 dB point, P-O-I-N-T, the 3 dB point. It is the point where the gain is at minus 3 dB. It is the frequency at which the gain is at minus 3 dB. So that's what I'm talking about here. And so this is just a convention, but there's some rationale behind it. Basically, it's got several names, and so the 3 dB point has several names. It's obviously called the 3 dB point, or the minus 3 dB point. That's one name. Another name, and this is the one I'm going to come back to, is the half power point. That's the half power point. It's also called the break point frequency. It is definitely called the cutoff frequency. And it's also called the corner frequency. And you will see that corner frequency in EE, I believe, 10. And it is when you start doing an approximation to the Bode plots. You can see that in this the Bode plot is a nice smooth curve a lot of times, but you can approximate these curves with straight lines. And so where the straight lines meet is one of the points where they meet is at the 3 dB point. So it's called the corner frequency or the break frequency for that reason. So it's got these several names. And like I said, the one that I'm going to be spending a little time on is called the half power point. And it's called that because power is proportional to the square of voltage. You know, power is V squared over R, right? It's 1 over R times V squared, and it's proportional. So if the power is half, if P equals 1/2, then it's because the half power point. If P equals 1/2, then V must be 1 over square root 2, which is the same as 0.707. And so the 0.707, the 70% point, that is an important point because that is the half power point of the signal of the filter, and so that's where they're saying, you know, above the half power point we're in the stop band, below the half power point we're in the pass band. It's just somebody decided and people agreed. So that's basically what they're doing there. And the other point of this is that if you want to put this on a dB scale, then the dB equivalent of 0.707 is 20 log 0.707. which happens to be minus 3.01 dB. So there you are. You know, that's how all of this ties together. This 0.707 minus 3 dB, half power, all of that stuff just kind of fits in that way. Okay, so I mentioned the 45-degree point in the phase shift. That would be this right here. The question is why? Why is it important? Well, if I draw the circuit, it'll be and do a little analysis here, it will become apparent why it's that way. I come along here. Here's the circuit. I have some resistance here, some C value there. This is VI and this is VO. And I can write a voltage divider equation that says VO equals VI times 1 over J omega C over R plus 1 over J omega C. And I can do the ratio of output to input, which, as I mentioned before, is called the transfer. Loosely called the transfer function. So it's output over input. Then if I multiply by J omega C, numerator and denominator, I get this, 1 over 1 plus J omega RC. And so now the question is, when omega equals 1 over RC, then V out over V in equals 1 over 1 plus J1, right? Well, if we were to look at just the magnitude, which would be the yellow curve here, this magnitude up here, then the magnitude of this, and it takes just a tad amount of algebra, but the magnitude is, and I'll leave that for you to work out, is equal to 1/2 minus J 1/2. And when you plot that, you plot your complex values on a real versus imaginary scale, And sorry, I got those backwards. Let me undo those. Real, and the x-axis imaginary versus real. And so you get something that looks like this for 1/2 minus j 1/2. It comes down here, and this would be 1/2 here, and then this would be minus 1/2 here. And I'll extend that line down, minus 1/2. And so, what is the length of this line? What is the magnitude of this? Well, it's basically it's 1/2 squared plus 1/2 squared, and the square root of that. So that's 1/4 plus 1/4, and that's 1/2. So what is, and the square root of 1/2 is 1 over square root 2, which is 0.707. So the magnitude is 0.707, and what is this angle here? Well, this angle is minus 45 degrees. So now we go back to the picture here, and that's why you can find the 3dB point. You can find it by looking at where the phase shift crosses minus 45 degrees when you're talking about a low-pass filter. Clearly, if it's a high-pass filter, then you could look at where it crosses plus 45, but then you just come down and you read off the frequency. So that's a fairly easy way of doing it if you have a first-order filter. That is, okay, so I have just one other idea that I want to explain to you. We have said here that omega, we've said this is all the case when omega is 1 over RC. That gives us this half power point. And so what that really means is that the when omega, this is, and I'll just give it a name, omega sub c, when that equals 1 over RC, that is the cutoff frequency, C for cutoff. And that means that, of course, if we want to talk about the cutoff frequency, that is 1 over 2 pi RC. And this is the theoretical value. It's a function of the resistance and the capacitance. And that will give you the theoretical value of the cutoff frequency, and now you can compare it to the frequency that you get by looking at where the line crosses the minus 45 degree, and that is basically what is going on with the Bode analyzer. And yeah, thank you for watching.